Hello everybody, my name is Pantelis, and I am co-founder and vice president at Fusion, a computer vision and machine learning startup based in San Francisco. Today, I will talk to you about building complex geometry and 3D experiences rendered entirely in CSS and HTML, and how using such a node-limited approach can actually help us be more creative. Right off the bat, there are two big questions that need to be addressed. The first one is, define complex 3D geometry. Can we actually build full 3D worlds with CSS and HTML? And the answer is yeah, certainly. Everything you see in this scene is built using traditional HTML CSS and JavaScript just for state control and navigation. For example, the candle flame is a mix of layered box shadow animations. The lighting and shadows are computed semi-dynamically and rendered using background blend modes, and you can even see that there is like a creature roaming on the floor. So taking a closer look, we can see that the moon is just a div with border radius applied, and we can also render the wireframe of our geometry by applying a 1-pixel border through the developer tools. Everything I will show you is open source and will also provide links to examples and source code. Now, the second question is why? Why even bother with something like this? There is WebGL, GPU accelerated canvas, and WebGPU is almost here. Why limit ourselves in building 3D with CSS and HTML? To answer this question, we need to study a bit an interesting concept named constraint creativity. I'll take you a bit back in time when I first encountered this. So, I've been writing JavaScript since around early 2001, and the truth is I didn't get started by choice. So I got my first computer back then and started tinkering with web development when I discovered the view page source button in Internet Explorer 5. So naturally, I soon wanted to build my own fully dynamic website. But back then, things were a bit different. The front end was deemed a thin client, and the heavy lifting would happen server-side. Now, I was just a kid in Greece, and I had no access to a server or a hosting platform. I had no credit card. My parents didn't believe in credit cards, and also putting your personal information online back then was considered a big danger. It's kind of like today, with all the privacy breaches. I guess we came full circle. But I stumbled upon JavaScript and noticed that it can be used for some interesting things like cursor effects or blocking right-click to prevent somebody from downloading an image. But more importantly, it could be used to manipulate elements on a page. So I wrote a single-page application fully in JavaScript that used nested iframes, passing data through the window.parent object to simulate asynchronous fetch requests. So what you're seeing over here is Windows Millennium Edition compiled to WebAssembly. And all this is running inside Chrome, and now inside Windows, we're running it in Explorer 5 that is running some code from like 20 years ago. And you can see it's kind of a cringy text-based adventure. So of course, single-page applications are commonplace today, but back then that was considered pretty extreme. So this idea stuck with me through the years, that when you have no clear way to do things, you're going to innovate. You either can give up or pave your own way and find something new. So it turns out this idea is somewhat well studied, and I'll mention two brief examples I find very inspiring. So Igor Stravinsky was one of the most prominent composers of the 20th century. Stravinsky was a big believer that in order to excel at your craft, you need to challenge yourself by imposing hard constraints and pushing and breaking through them. His most famous piece is called The Rite of Spring, and it uses no conventional rhythm patterns. It actually has more than like 440 tempo transitions. And what was the result of that? Well, according to myth, there was a riot during the premiere. Like, people just couldn't handle how different it was for the time. Now, history has decided that it is one of the most important contemporary musical works. Cool. So Ernest Hemingway also flirted a bit with the idea. He bet that he could create a meaningful story in just 6 words. Well, spoiler alert, he won the bet. And the idea took a life form of its own and spun off to multiple variations and competitions with established and amateur authors participating. My favorite one is Alien Guns. Computer, did we bring batteries? Computer. So this fun challenge approach is hailed as a quick way to break through writer's block and generate ideas quickly. So this is the concept of constraint creativity, and I found this fascinating, and my worldview changed a bit. So most people think that hard constraints greatly suppress creativity and forcefully guide our way of thinking to very specific and right paths. However, research demonstrates the opposite to be true. When the approaches are infinite, we tend to get stuck and face choice paralysis, or the tyranny of choice as it's called. But when options are limited, we tend to generate more rather than less varied ideas and solutions. So this is the concept of constraint creativity. In a sense, it's easier to think outside of the box when the box is very well defined. So with that being said, naturally, let's go build 3D geometry with HTML and CSS. So the main component we will be using is 3D transforms. 3D transforms allow us to translate, rotate, and scale an element in 3D space. They also have some interesting properties. They're GPU accelerated, which means they're pretty fast, and they do not modify the DOM's flow model. So for example, translating an element will not push or modify the elements around it. So let's try to translate an element across its z-axis. We notice that nothing really is happening. However, if we rotate the scene and look from the side, yep, we see that the element does move on the z-axis properly. We would expect it to appear smaller as it moves away and bigger as it comes closer. So this is called perspective, and it is a depth distortion model that aligns with how we humans perceive the world. And I use the word distortion because it might seem natural to us, but it's not exactly how the world is supposed to work. So take, for example, parallel lines. We've all read in school that parallel lines can never intersect. But if we sit in the middle of a road and look straight, we see that the parallel lines, the lanes, seem to converge at the horizon point. This illusion, of course, they don't really converge, it's an illusion. So this illusion is due to our eye's curvature and receiving bouncing light rays from multiple directions. So this is called perspective. Luckily, we have a way to do this in CSS. There is a CSS property, aptly named perspective, that does just that for us. So its value specifies how far the z-plane spreads. If a small value is given, it will add a lot of depth distortion, but if a larger value is given, then it will add less. Now it all looks as expected. So the next part and the first problem we encountered is how to add a camera in our scene. In traditional graphics, we can have a camera actor object that navigates the scene, and we can render the world from the camera's viewpoint. Unfortunately, we cannot do anything like this in CSS, but maybe we can approximate it. So maybe we can use an intermediate HTML element that will contain our world. So now our structure becomes like this. We have a wrapper element that will be basically our screen or our window to the world, and needs to have dimensions set, as well perhaps overflow hidden or constraint strict to hide the world outside of it. Inside it, we'll have our camera element, which will be positioned at the center, and of course will be absolute. And inside the camera, we will have the rest of the 3D HTML elements. We also might want to split the camera element across multiple objects in order to make some math and transforms easier. For example, we can split rotation and translation. And we can see exactly the HTML, how it's going to look. We apply our perspective to the viewport element, we have the camera rotation, and then the camera translation. And we can also see a demo how it works when the transform values change for rotation and translation respectively. So what happens is that when we look around, it's not us looking around, it's the whole world moving around us. It's like, imagine you're doing a push-up, and rather than lifting yourself up, you're just pushing the whole earth down. But it works pretty well. So with just this knowledge, let's try to build something in 3D. So what we have here, it's a little bit of a low-effort Mario Kart clone, and you can see that it can switch between 2D and 3D mode, and also the HTML that we have in the scene. So again, we add perspective to the viewport, we have the camera that's centered in the middle, and it's absolute positioned, and then we can do the following. We can just rotate the camera on the x-axis, and we have successfully switched from 2D to 3D mode. Then if we want, we can chain a translation to the rotation, so to get closer to the camera and make it look as a nicer third-person mode. And then we can make the card stick up by applying the reverse transformation that we apply to the camera. And that's it. So now let's look at some other interesting properties. Its transformation is also affecting the element's coordinate system. What this means is that the next transform will depend on the previous one. So to better understand this, imagine you're driving your car and the GPS asks you to drive straight for a mile and then turn right. Now, if you decide to outsmart satellite-based navigation and turn right first and then drive straight for a mile, you'll end up in a completely different place. So this is the importance of order of operations. Usually, it's useful to follow a certain logic, like rotation first, translation second, and scale last, as things can get complex with mixing different things quickly. Now, there is a problem. What happens if we keep driving around? Like we turn left, drive straight, whatever. So we will be accumulating transform after transform, and may end up with a very long CSS transform string. So luckily there is a way to flatten a transform and represent any possible transform with a single data structure. This is called transformation matrices. a transformation matrix is a mathematical linear algebra concept that can be used to represent a full 2D or 3D pose of an element. And we also happen to be even luckier because there is a DOM API that already handles the heavy lifting for us, the DOM matrix API. So you can instantiate a DOM matrix object and pass to it a CSS transform string. For example, translate 3D, rotate, translate, blah, blah, blah. And what we get back is a 4x4 matrix representation of it. And if we replace the transform string with a matrix, we see that it aligns. We get the same transformation out of it. Now, the final concept we will explore is that of a scene hierarchy. What basically means that the transformation of an element is dependent on the transformation of its parent elements. To give you an example, you can extend your finger and notice the position of its tip in absolute space that it's pointing. Now, if you rotate your elbow, your finger's position in absolute space has changed, even though your finger itself didn't move at all. So this is what we call world coordinates or an absolute space system. Now, if we speak to a physicist, they'll tell us there is no such thing as absolute space. Everything is relative to something else. Your elbow is relative to your arm to your body, body to earth, earth to the sun, etc., etc. But luckily, we're web developers and get to define what absolute space means in our scenarios. So again, in our previous example, we have a problem. How do we find our finger's new position after we rotated our elbow? And again, transformation matrices save the day. So what we need to do is we first need to represent the original positions of our vertices as 3D vectors. So top left, which was 0, 0, now will be 0, 0, 0. And for bottom right, which was like equal to width and height, now will be width, height, 0. The z-axis is always 0 since in our initial position, we were operating on 2D space. Then we can grab the transformation matrix of our element, and we can do this by using the DOM matrix API. So we feed to it our transform string and get a matrix back. And then all we have to do is multiply the 3D vectors we created with the transformation matrix. And this is it. We get new XY coordinates after this operation, and we can set them as translate 3D transforms, and we can see that now they match the new position. So what we have done is we did the local to world coordinate transformation. So let's put everything together. This is important because by knowing how a position has moved in space allows us to chain elements together and create a scene or an object or, for example, a room with just divs and HTML elements. So we see that it works, but it looks kind of ugly. It looks pretty flat. And we can even add textures, which we can do with background images, but it still looks pretty ugly. And this is because we can't sense depth. Our screen is 2D, it's flat, so our multi-view depth perception fails. However, our brains still do a fantastic job at estimating depth when looking at 2D-dimensional images. And this is so because our brains rely on the flow of light and shading in a scene. So we need to find a way to add shading in our scene. Now, unfortunately, there is no clear way to do this in CSS, but we can borrow some tricks from traditional 3D graphics. We need to compute what is called a face normal. A face normal is a vector that lies in the center of our element and it's perpendicular to its surface, pointing outwards. So then all we have to do is we need to compute the angle of our light's direction against that vector. So if it is 0 degrees, it means that light falls straight right on the surface, so it's fully lit. If it's at an angle, then we compute a value between 0 and 1, and that will be the light's intensity for that surface. If it is 90 degrees, it means that light goes parallel to the object, so it's not lit. And if it's greater than 90 degrees, it means that light hits the back face of the object, so again, it is not lit at all. And we can put everything together and render light maps and mix them with blend modes and get this. Nice. Now, let's take it to the next level. I promised you complex 3D things, so let's try to do something more crazy. Shadows. So again, there is nothing we can use in CSS for shadows. Box shadows are nice as backdrops, but cannot really be extended to represent any light source. So what we do is we do ray casting. So we cast from our light rays and check to see if they hit a surface or if there is any element between them. If there is an element between them, we mark that pixel as dark. And we can even add some blur to make our shadow a little bit smoother at the sides. And we can see that we can also have multiple shadows, so this can actually work pretty well. Now, what if we want to do something even more crazy? what if we want to mix real volumetric 3D with our fake CSS 3D? You can see the end result. We have a creature that's fully shaded and naturally blends in our scene. The way we're doing this is with billboarding. Billboarding is a technique that adjusts an object rotation so that it always faces the camera. All video games will use this as an optimization. For example, there would be like a paper-thin tree that in any way you rotated the camera, it would always face you, so that they wouldn't have to render like a full tree, because trees can actually be pretty complex to render with all the leaves and detail. So this might seem crazy wasteful that now we have a WebGL renderer moving in our scene as a 3D object always facing the camera, but this is very similar to how augmented reality rendering works. See, this is like an industry secret about augmented reality. Augmented reality is just graphics in reverse. In traditional graphics, we know the camera pose, and the question is, how do we figure out how to render the world in front of us? But in augmented reality, the problem is the opposite. We know the world, it's the real world, and we want to figure out the camera pose, because knowing the camera pose and trajectory means that then we can render any 3D object we want on top of that world. So, for example, and another problem, of course, is light estimation. So if we want an object in augmented reality to be properly lit, we need to represent the world's light source, for example, the sun. And that's exactly what we did in a CSS game. We represented our CSS lights in the WebGL world. So what about performance? So performance is actually pretty good. We can hit 60 FPS even on older mobile devices. I've throttled it to 30 for improved battery life. And there are some tricks we can utilize, for example, multiple level of details or geometry culling, which basically means we can remove anything from our scene that is not currently visible on the screen. Now, what if we want to go even a step further? Let's break this constraint completely. So, we've all seen traditional 3D models, and they consist of triangles. The reason they consist of triangles is because you can represent any 3D plane with just 3 points. Now there is a problem. In HTML, we only have rectangles, and they're not even scalene rectangles. They have, even though they have four vertices, they can be represented by only 2 points: the origin point and then width height. So we need to somehow create scalene triangles from such a constrained structure. So we start backwards. We split the 3D triangle into 2 distinct concepts. One is the 3D plane, as we mentioned, defined by its triangle's 3D points, and this plane expands to infinity. It's a concept, it's not a real thing. And then we need to get the triangle shape, which will normalize to 0, 0 coordinates, and it will project it in 2D. So the shape itself will not have depth, but it will be aligned on that 3D space. And we can see it right here. So we create our element, and we align it with the triangle's 3D plane, and our goal is to get one of the sides of our rectangle to match a side of the triangle. And then we add a child element projecting 2D, and we want one of the edges of that element to match with the third edge of the triangle. And then we simply set overflow hidden, and that's it. We have a scalene triangle. And being able to have scalene triangles allows us to render any shape, any 3D model in CSS. And as we mentioned, we can add shading and lights and have it look pretty cool. So what do we learn from all this? Well, CSS and HTML can be pretty damn powerful, that's for sure. We started thinking that we would become blocked very quickly, but we were able to break through every single obstacle and come up with very creative solutions like billboarding, background blend modes for lights, etc. So we gained knowledge about 3D math, matrices, transforms, and scene hierarchy. And we also figured out some optimization techniques that can transfer over to 2D interfaces. But what is really interesting about this is that it can be a great way of introduction to 3D because it uses familiar concepts like CSS, CSS Transforms, and the toolkit is basically the developer toolbar that we use every day to debug a website. So the hard part about learning 3D is because it's such a vast world. There is such a big corpus of literature, and getting started is actually pretty difficult. There is linear algebra, there is all the mathematics, there are concepts like shaders, GLSL, vertex shader, fragment shader, all the triangle-based logic. Then the toolkit is different, like how do you debug a shader, how are you able to control the GPU? All these things are pretty complex. So this way we can actually build a bridge and cross the two worlds by getting an introduction by using concepts that we already know. And of course, we improved our skills and now our understanding of CSS transforms and APIs such as the DOM matrix. So Stravinsky was right. We can become better in our craft by challenging ourselves with constraints. Now, somebody might say, why be constrained? Why focus so much time on a singular thing when there are so many technologies, frameworks, infinite things in the ever-evolving world of technology? And the answer to that is that this concept of infinity is a fallacy on its own. Even if technology is boundless, we by nature are not. We have limited time per day to learn new things. We might have a very time-consuming day job or limited budget. We might be tired and have limited willpower to challenge ourselves and learn new things. And we can see this historically too. Even if technology spreads and grows and we can come up with amazing future-facing science fiction concepts, the way we interact with technology hasn't changed a lot. We had typewriters like 200 years ago, then we got keyboards in the 1960s, and we use the same keyboard layout today. All the futuristic things we create in the end are still limited by the anatomy and physiology of our hands, or for example, the perspective projection of our eyes. So it's very interesting. Despite all these very rigid and universal human constraints, we are still able to break through, innovate, and creating amazing work. And then, on the other side of the fence, are our end users, who come with their own and even larger spectrum of constraints than any of us may have. They might have accessibility issues, they may have weak or old hardware, slow internet connection in a remote area, 1% of battery life left, limited familiarity with technology, speak different language, just to name a few. The list is never ending. But yet, it's under their framework of constraints that the output of our work will be evaluated. So this way, we get closer to a final iteration of this thought, to a secret truth, that it is not only despite constraints that good work is created, but also because of. Thank you.
Oh my goodness, I'm in awe at your talk. Thank you so much for that.
Oh, thank you. Hello, everybody.
Wow, oh my goodness. I have so many questions, but we don't have all the time in the world as much as I want to, but the audience has some great questions for you as well. And so with all of this math, there's all kinds of linear algebra and things happening here. Are there any frameworks that exist or that you can recommend that might help with some of these calculations if we wanted to try it ourselves?
Yeah, so there are actually quite a few. The most famous one is Three.js. You can actually use Three.js and not touch the WebGL parts. You can just use the great linear algebra math. Yeah, they have like the matrix structures, the quaternions, so they have everything. Then there are a few a little bit more bare bones, like there is Sylvester.js that has been around like for 10 years. But that math hasn't changed. That math is the same math NASA used like in the 60s, to send rockets to space. So it's just set to stone.
Just so much math. I love it. That's so cool. And I actually didn't realize that you could use Three.js without WebGL. So that's really cool as well. Have you explored any... Oh, go ahead. Go ahead.
No, please. I was going to say that Three.js actually has multiple renderers. There is an SVG renderer, a canvas renderer, and there was actually a plugin that allows it to do like an ASCII rendering. So you have text, and they use like ASCII art to represent 3D models. Yeah, it's actually pretty cool.
That's incredible. Oh, I'll have to play with that. That is so neat. Ooh, I'm nerding out over this. Have you explored any performance limits on any of these projects, like frames per second and stuff? Is there a point where you start to lose that smooth transition for everything and it starts to get a little laggy?
Yeah, heavily. So as I mentioned, we can have around 700 to 800 faces. And by the term face, I mean like an HTML element, but it also depends what we put inside them. Like if you use like a 20,000 pixel texture, it's going to be way heavier than just using a background color. But there are also multiple tricks. Like a very common trick is to hide. You can set display none to everything that is not visible on the screen. So you can do some math and say, is this element like behind me? if that element is behind me, there is no point in having it actually in the scene. And another thing we can do is if an element is far away, maybe we can display it with lower fidelity. Like we can use a lower lower resolution texture. That is called like LOD, multiple levels of detail, and the previous one is called like geometry culling. Like for example, in the demo I have created, like if you move far away in the first room, the candle flame is no longer animating. We're pausing the CSS animation on the flame because it doesn't really make sense. No one is going to notice that the flame is not moving from far away.
Right. That reminds me of just all kinds of video game development things. I remember with the game Breath of the Wild, they did such a cool way of rendering things far away where it was just not only a little bit fuzzier and lower resolution, but also just they kind of put a light sheen over it so that way it just looked far away, like there were clouds in the distance or something to block it. And it's a really cool effect.
Yeah, that one is a very smart trick, yeah.
Yeah. And so one last question before we start to run out of time. Do you ever handle multiple users in a 3D world that have multiple perspectives? Have you dealt with that kind of mask before or that kind of use case?
I have not really dealt with that. So if you want to do something multiplayer, we could do it. There is no reason not to. But if you want to have multiple cameras in the same world, because we're kind of limited, like this is just an HTML element with other HTML elements inside.
Yeah.
It would be even more hacky than it is to do it now. But hey, if someone wants to try, like I would be super excited to see the result.
Me too. I'm curious if you were to have, like Mario Kart split screen style, but just on the same screen with the same stuff. It would be interesting to see how that would work.
That could happen. It would need to have like double the geometry, since we can't really mirror everything. Whereas with a WebGL-based solution, I mean, it would also render everything twice, but at least like the underlying geometry is only loaded once in the memory.
Right, it would just be two cameras.
Yeah,
that makes a lot of sense. Well, anyway, thank you so much for your talk. Every single person in the chat was just like, "Are you kidding me?" So it was so cool to see. I loved being able to watch this and geek out over it. So thank you so much for being here today.
Awesome. Thank you, Cassidy. Bye.
Bye. And up next we have Amber coming to speak. Let's go.